us discuss some basic properties of the derivative map. The proofs of these are rather easy. They are modeled on similar proofs we have been seeing from high school. First, let's start with the proposition. This just says that the derivative is linear in a different sense. Linearity of the derivative. We already know that the derivative is a linear map, but this is sort of saying that taking the derivative and treating it as an operator, that itself is linear. So the setup is as follows. Let U subset of E be open, and let F comma G from U to Rm, or rather F in our notation, to F be differentiable at X in U. Then F plus G is differentiable at X, and d of F plus G at X is just dfx plus dgx, and in the entirely similar way, d of Cf at X is just C times dfx. So treating the operator D as taking a function and outputting a linear map, that itself is linear on the space of differentiable functions. So summarizing, the derivative operator is a linear map on the space of functions differentiable at X. Okay, so the statement is really long. The proof is going to be rather easy. So this is one of those scenarios where all the work has been done over the years. So what is the meaning of f and g are differentiable? We just write down f of x plus h is going to be equal to f of x plus dfx h plus an error term which we call e1 of h, and in an analogous way, g of x plus h is g of x plus dg of x h plus e2 of h. Okay, now e1 plus e2 is obviously sublinear. The sum of two sublinear functions is going to be sublinear. e1 plus e2 is sublinear, so immediately we get f plus g of x plus h is equal to f plus gx plus dfx plus dgx, the whole thing acting on h, plus e1 plus e2 of h, and we are done. This just, the whole thing can be summarized by saying that the sum of two sublinear functions is sublinear, and the same thing is going to happen for the scalar multiplication case. I'm going to leave it to you. It's an easy check. Okay, now the next thing is we have dealt with sum and scalar multiplication. The next question to be asked is, what about product? Well, the issue is there is no natural way to multiply two vectors in higher dimensions. You can do it in special cases. There is a thing called the vector product, which you would have studied in school, but I want to generalize this notion of product in the following way by defining what is called a bilinear map. I'm sure you're familiar with bilinear forms from your course on linear algebra. You might have studied bilinear maps also, and the definition is not that hard. So the setting is as follows. Let E comma f and g be vector spaces. A bilinear map is a map B from E times f, the Cartesian product of two vector spaces is in an obvious way a vector space. It's a map from the product E cross f to G such that for any fixed y in f and fixed x in E, both the maps, so you fix the first slot to be x and treat the second slot as a variable, so you will get a map from f to G, and you treat the second slot, you treat the first slot as a variable and the second slot is fixed, so you get a map from E to G. Both these maps should be linear, such that both these maps are linear. So bilinear mapping is just a map that's linear when both variables are fixed. So an easy exercise for you is the following: show that any bilinear map on Euclidean spaces. So E, F and G are Euclidean spaces. On Euclidean spaces is continuous. Bilinear maps are automatically continuous. Okay. So now with the notion of bilinear map at hand, we can state and prove a very simple product rule. It's quite general, but at the same time the proof is not hard. So the setup is, let E, F1, F2 and G be Euclidean spaces and B from F1 times F2 to G be bilinear. Let this be bilinear. Okay. Now given maps F1 from U to F1 and F2 from U to F2 differentiable at x in U, then the map B of F1x, not F1x, I will use F1y, comma F2y. This is a map that starts in U and you land up in G. This map is differentiable at x. So essentially we are taking a generalized product of F1 and F2 via this bilinear map B. Is differentiable at x, and the derivative surprisingly is given by phi of h, and the derivative is phi of h takes h to b d fx h comma f1x comma f2x plus b f1x comma d f2x h. Okay, so this might look a bit surprising, but if you think about it, this whole thing is nothing but the standard Leibniz formula for the product. Think about this for a while, why this is the standard Leibniz formula for the product. So essentially the same product type rule holds even in this quite an abstract and general setting of bilinear maps and all that. Okay, now let's prove this, and the proof again is not that hard. The statement is quite complicated, but the proof is not hard. The claimed derivative map is indeed linear. I want you to check this. That's quite easy. You just have to use the fact that the place where h occurs, there is a linear map in front of it, and B of course is bilinear, so everything will go through. Okay, so is the claimed derivative map is indeed linear. So let E1 and E2 be the sublinear functions coming from the definition of differentiability of f1 and f2 respectively. So f1 and f2 are differentiable, so you have, I'm getting a bit bored of writing the same thing over and over again. So you will have f1x plus h is equal to f1x plus df1x h plus e1h, so on and so forth. Okay, now we'll have to do a straightforward but somewhat long computation. Each step is going to be utterly simple and modeled on the high school proof for the product rule. So what do we have to compute? We have to compute b of f of x plus h, sorry, f1 of x plus h, comma f2 of x plus h minus b of f1x, comma f2x. We'll have to compute this. And as usual, we add and subtract an appropriate term to make things go through. So we just write b of f1x plus h, comma f2x plus h, subtract b of f1x, comma f2x plus h, then add back this term which is b of f1x, comma f2x plus h, and finally we add the original minus b of f1x, comma f2x. So this is the standard add and subtract, the combination of the quantities that you require. Okay, so now this just is equal to b of f1x plus h minus f1x, comma f2 x plus h. What has happened? Well, these two terms have been combined together by bilinearity. In a similar way, we are going to combine these two terms by bilinearity. So you will get plus b of f1x, comma f2 of x plus h minus f2 of x. So we have just applied bilinearity twice to combine certain terms. So we have the term of the required shape. So let's apply the definition of the derivative to both f1 and f2, and we immediately see that we get b of df1x h, comma f2 of x plus h plus b of f1x, comma df2 of x h. Okay, and of course I must add the error terms, so you will get b of e1h, comma f2 of x plus h. Of course I'm tacitly applying the bilinearity, plus b of f1x, comma e2h. So I have combined two steps. I have expanded out f1 of x plus h minus f of x and f2 of x plus h minus f of x and applied bilinearity. Now notice that the first term is almost exactly what we want, except there is an additional h here which we don't want. Okay, other than that the first term is perfect, and the second and third term, the third and fourth term are also almost exactly what we want. So we are going to show that the third and fourth term are sublinear in any case, but before that we have to somehow fix the first term which has an additional factor of h. So this is nothing but doing the same trick again and again. This is the same add and subtract trick. You can check that this is nothing but b of df1x h, comma f2x plus h, f2x plus b of f1x, comma d2fx h plus b of e1h, comma f2x plus h plus b of f1x comma e2h minus b of d f1x h f2 of x plus h minus f of x. So this last term is the thing that does the job for us. These two combined together, these two terms combined together would just give this term. Okay. So we have done the required manipulations. We have got the first two terms to be exactly what we claim is the derivative, which I have asked you to check is linear. So our job is to now show that these three terms are sublinear. So I'm going to say this final term, sublinearity is very easy. So this is sublinear, is very easy. It just follows from continuity and linearity. It will just follow immediately from continuity and linearity that this term is sublinear. Okay. So we have left to check that these two terms are in fact sublinear. Let's just focus on one of these terms and show that it's sublinear. The other one is exactly going to be similar. Okay. So let's focus on this second term, b of f1x comma d e2h comma e2h. Let's try to show that this is sublinear. So we have to divide by norm h and see what happens as h goes to 0. Well, by linearity of the bilinear map, I can just write this as b of f1x comma e2h by norm h. Okay. Now when I take limit h going to 0, I can push the limits all the way inside simply because b is a continuous mapping. So because b is a continuous mapping, I can put the limits inside. So this is nothing but b of f1x comma limit h going to 0 e2 of h by norm h, and this is nothing but b of f1x comma 0, which is just 0 by bilinearity. Okay. In a similar way, you can show that the other term also goes to 0. So we are done. We have shown that whatever remains is the error term is nothing but a sublinear function. Therefore we are done. Okay. So the product rule is also easily dealt with exactly like the way we did in high school. So one final property of the derivative, which is modeled on our high school studies, is the chain rule. And the chain rule, again, the proof is going to be a bit tedious, but the basic idea is very simple. So the setup is as follows. Let E comma F comma G be Euclidean spaces. Let them be Euclidean spaces, and let U subset of E and F subset of V subset of F be open. Okay. Now suppose F from U to V and G from V to G are differentiable at x in U and f of x in V. Then G composed F is differentiable at x with derivative dg composed with fx is nothing but dg of fx composed with dfx. This is the linear map which is going to be the derivative. Okay. So the proof is going to be rather mechanical, but it is straightforward. So what we are going to do is the following. Let E1 and E2 be the sublinear functions coming from the definition definition of differentiability of f and g. Okay, so what this is essentially going to mean is that f of x plus h is f of x plus dfx h plus e1h, and g of f of x plus k is equal to g of fx plus dg at fx acting on k plus e2k. Okay, now we are going to set k to be nothing but f of x plus h minus f of x. As usual in most proofs of chain rule, we have to do something like this, and we have to compute what g of f of x plus h minus g of f of x is to get what we need. Okay, so g of f of x plus h minus g of fx minus g of fx is nothing but g of f of x plus k, because k is nothing but f of x plus h minus f of x. F of x plus h is nothing but k plus f of x. Okay, so this is nothing but g of f of x plus k minus g of f of x. Okay, which is going to be or rather let me just write it as this is equal to, let me take it to the other side, this is equal to g of f of x plus dg at the point f of x acting on k plus e2 of k. Right, so far nothing but basic algebraic manipulations, and this is nothing but g of f of x plus dg fx, and k is nothing but f of x plus h minus f of x, so this is nothing but d f of x plus e1h. Okay, this is dg of f of x acting on the vector dfx plus e1h plus e2 of k. Okay, so we have got something very similar to what we want. We have got this term g of f of x, and we have got dg of f of x at the point f of x acting on dfx plus e1h plus e2 of, I missed a h, that was what was throwing me off here. This is actually h plus e1 of k. Much better. So we have essentially got what we need. What we have to show is, we have to show that this term dg at the point f of x acting on e1h and e2 of k are both sublinear, and here the variable is h, not k. Okay, with respect to h. Okay, so what we have to show is e2 of k and e2 dg fx at e1h are both sublinear. Let's take care of e2 of k first. Let's look at e2 of k by norm h. This is nothing but e2 of k by norm k into norm k by norm h. Okay, and this is less than or equal to e2 of k by norm k into norm dfx operator norm times norm h plus norm e1h divided by norm h. I have just expanded out what norm k is, which is f of x plus h minus f of x, which I am just expanding out by the definition of the derivative and then doing some basic properties of like triangle inequality and the basic properties of the operator norm. Okay, now as h goes to 0, as h goes to 0, this second term obviously goes to 0. This second term obviously goes to 0. Okay, as h goes to 0, k goes to 0 as well, and second term goes to 0. Second term goes to 0. And because as h goes to 0, k goes to 0 by continuity of f at the point x, the first term also goes to 0. Okay. Now, there is one crucial thing that has to be remembered. We have made the assumption that k is not 0 as h approaches 0. But that's not really an issue, because what was the original expression that we were interested in? We were interested in this expression, E2 of k by norm h. If for some value of h k happens to be equal to 0, E2 of k is going to be anyway 0. Okay, so as you approach h going to 0, we need to consider only those points where k is not 0 and estimate what happens, which is what we have done. So this division and multiplication by norm k, which was crucial for the proof, is actually justified, because at those points where k happens to be 0, we already know that this entire thing is 0. No more estimation needs to be done. Okay, now only one term remains, that's this dgfx e1h. That this term is actually going to be sublinear is obvious and is left for you to do. So the proof of the chain rule was a bit involved, but it's straightforward. You just have to be a bit careful. It's essentially one of those proofs where you just write down what you have and just start working it out. You will eventually get the proof. This is a course on real analysis, and you have just watched the video on the properties of the derivative map.